So this is a question, and the parallel plate of the formula you need to take note: C is equals to Q over V. Surface charge density equals to Q over A. Then electric field between infinite plate equals to surface charge density over permittivity of free space. And you should know that V equals to the electric field times distance ED, and you should know that C equals to um, E naught A over D. I've proven those things, but just keep those one in your mind, at the back of your mind. So the parallel plate of a 1.0 farad capacitor are 1.0 millimeter apart. Show that their area is 1.1 times 10 raised power 8 meter square. The volume of this capacitor is 1.1 times 10 raised power 5 meter cube. So we know C is equal to E naught A over D. So what's our C? 1 farad. 1 equals to E naught. Permittivity of free space is constant. 8.85 times 10 raised power minus 12. That's permittivity of free space. So you should know that one times area over E naught over D. What's our D? Our D is 1 millimeter. Convert it to meter. You have 1 times 10 raised power minus 3 meter divided by 1000. So you cross multiply. Your A will give you 1 times 10 raised power minus 3 divided by 8.85 times 10 raised power minus 12. So if you punch your calculator, yeah, true, you are going to get 1.1 times 10 raised power 8 meter square. So it's correct. Now to show the volume, volume equals to area times density. So 1.1 times 10 raised power 8 times distance rather. What's the distance? 1 times 10 raised power minus 3. So we are going to get 1.1 times 10 raised power 5 meter cube. So that's correct. Now, another question we are going to treat now is this. Sorry. There is a mistake in this question here. So let me just cover it so that you won't be confused with that. So that's not part of the business you are dealing with now. So this is the question we want to solve. Are we together? So the parallel plate of a capacitor in a vacuum are this. The parallel plate of a capacitor in vacuum. The question should be the distance between the parallel plate of a capacitor in vacuum. Yeah. Okay, yeah. Okay, I've seen what I'm looking for. The parallel plate of a capacitor in vacuum are 5.00 meter apart. Yeah, that's correct. The question is correct. Apart. So that means our distance equals to 5 millimeter. 5 millimeter. I have an area of this. Our area equals to 2 meters square. If the terminal of a battery, 100.0 kilovolt battery, are connected across it, show that the capacitance is 3.54 nanofarad. We are going to show a lot of things. So we are given battery V 10 kilovolt. Convert it to volt. That should give you 10,000 volt. So you multiply by 1000. So are we together? Now, we are also asked to find if our E is equal to 2.0 mega Newton per charge. So now, the first thing to show is our C. Now, let's find our E first, because that one is much more easier. V equals to ED. That means your E equals to V over what? D. Are we together? V over D. What's your V? 10,000 volt. What's your D? 5 millimeter. Convert it to meter. That's 5 times 10 raised to power what? Minus 3. So 10 over 5. 10 over 5 equals to 2. If this one goes up, you have 2 times 10 raised to power. Yeah, 2 times 10 raised to power 6. Yeah, you can do it, you get that. So 2 times 10 raised to power 6 Newton per C. The same thing as 2 mega. Mega is 10 raised to power 6. So our E is correct. or this 10 raised power 6 is mega, or 2 mega Newton per C. So our E is correct. So to find our C, okay, since we are given area, go far. Our C, we can find the C first. Sorry, I couldn't see that. C is equal to E naught A over D. Are we together? Permittivity of free space 8.85 times what's our area? 2. What's our D? 5 times 10 raised power minus 3. So where's my calculator? So this guy is 8.85 times 2 divided by 5. So this guy is going to give you 3.54. 3.54. This 8.85 times 10 raised power minus 12. Sorry, 3.54 times 10 raised power minus 9 farad. Yeah, and 10 raised power minus 9 is nano. So we're proving that is equal to this nanofarad. So that's for that. The last one, to prove that the charge in each plate is 35.4 UC. The charge in each plate is equal to 35.4 UC. Now, how do we do that? How do we prove the charge to be 35.4 UC? Now, let's use this. No, um, C equals to Q over V, which means that Q equals to CV. And since we have our C, 3.54 times 10 raised power minus 9. What's our V? 10,000 volts. Are we together? So this one will give us 3.54 times 10 raised power minus 5 coulomb, which is same thing as 35.4 times 10 raised power minus 6 coulomb. And the 10 raised power minus is the same thing as micro, so that's 35.4 microcoulomb. So we've proven that that's called 35.4 microcoulomb. So that's that for that. So now dielectric constant. We are moving to dielectric constant. So dielectric constant is inversely proportional to area. Inversely proportional to area. K to area. No, I'm sorry. Is directly proportional to area. K is directly proportional to area, but inversely proportional to distance. Are we together? Please take note of that. So you have our K is equal to C over C naught. Is also equal to E over E naught. So if you cross multiply here, you can have C to give you what? KC naught. Or you can also have E to give you what? KE naught. Am I communicating? So I will know that our C naught, that formula we used earlier, I'll take it as C naught, is equal to what? E naught A over what? Over D. Am I communicating? Yeah. If dielectric constant is directed to A, that means as A increases, the dielectric constant increases. But as D increases, it will decrease. So take note of that, please. So E naught A over D, that means our C, therefore our C equals to, since we have our C to be KC naught, and this is C naught, that means our C is equal to K E naught A over what? Over D. Do you get what I did? C is equal to KC naught from this formula. So and since E naught is this, so C will give us KC naught. KC naught. So and since our E is equal to KE naught, that means at the end of the day, C is equal to K C is equal to EA over D. No, KE naught is same thing as E. KE naught is same thing as E. So C is equal to E over D. This E is relative permittivity. So where E is our relative permittivity, our E naught equals to permittivity of free space. Our A is equal to area. Our D equals to distance between the plates. Our C is equal to the capacitance. Oh, this permittivity of the dielectric, not relative permittivity. Permittivity of the dielectric. Permittivity of the dielectric. Permittivity of the dielectric. This one is permittivity of free space of free space. Sometimes they will give you relative permittivity. They get relative permittivity. No, in this formula now, there's no relative permittivity is represented as ER. So, and relative permittivity is equal to what's it called now? I'm coming. What should be the formula? Yeah, yes, E over E naught. So you cross multiply your permittivity of dielectric equals to relative permittivity times E naught. Is this thing correct? I'm trying to figure it out. I'm trying to remember, and I don't have. Let me check the relative permittivity. Yeah, I think that's correct. So just know the formula when to use dielectric permittivity, when to use permittivity of free space, whatever you are being given. Do you understand? So when you have question, when you are given relative permittivity, and in the formula you only need the permittivity of the dielectric. Are we together? So you just know how to find the permittivity of the dielectric. That will be relative permittivity multiplied by permittivity of free space. So that's that for that. So now we are moving to, I'm going to check this. I'm going to confirm if this formula is correct. Then I'll put it in the comment section. So magnetism. Sorry, I'm so stressed out. I'm so stressed out. We do all of this in the tutorial that is coming up on Saturday before the test on Monday. So but I think I'm going to explain this magnetism very well. So what you need to know is that whenever you see star, that means it's going inward. Just imagine that somebody is throwing an arrow. This is an arrow. I'm throwing it inward. You are going to see the tail of the arrow. So the star represents the tail of the arrow. Are we together? So if I'm coming upward, you see the tip of the arrow. So whenever you see a dot, that means it's coming outward. Do you understand? Outward from the page. Whenever you see the tail star, it's going inward to the page. So for the direction of magnetic field. So let's leave this question for now. Magnitude. I want to base on the direction now. Now we know that something like this, you can see my finger. So Fleming's right hand rule say that whenever you stretch your finger like this, such that the middle finger and the forefinger are perpendicular to the thumb. This forefinger, this one is perpendicular to my thumb, and this one too is also perpendicular to it. Yeah, am I communicating? So the thumb will point, once you do your finger like this, such that this thumb is pointing upward, then the middle finger is pointing like this, and this one is like this. So the thumb is pointing to the direction of the force, this forefinger to the direction of current or velocity. When you are dealing with F equals to QBV. When you're also dealing with F equals to, for a conductor carrying current, F equals to BIL. So for this QBV, this is pointing to the direction of the force, this thumb. This one is pointing to the direction of velocity, while this is pointing to the direction of B, field. This tallest finger, middle finger, field. This velocity, and this force. Are we together? So this is it now. Am I communicating? So we are just going to, this is how we are going to do it. Now a wire of length. Now same thing, if you have BIL, this force, this field, and this current. The one for velocity in the first one is also for current here. So the other two remain the same thing. So now a wire of length L equals to 62 centimeter mass 13 gram is suspended by a pair of flexible leads in a uniform magnetic field B. So what's the length of our wire? We are given our length to be 62 centimeter, which is same thing as 0.62 meter. Is suspended by a pair of flexible leads in a uniform magnetic field B equals to 0.440 Tesla, pointing into the plane. What are the magnitude and direction of the current required to remove the tension? Now let's find magnitude and direction of the current. Now you are going to have, F equals to BIL. Let's find the magnitude first. So it's current. I will give us what? F over what? BL. Are we together? And what's our F? Mg over BL. We are given the mass, right? Which is something as what's our mass? Are we given mass? Yes, 13 gram. Convert it to kg divided by 1000. I multiply it by 10 to give you force. So 13 divided by 1000 times 10. So that's 0.13 over BL, 0.44 times 0.62. So 0.44 times 0.62, 0.13 divided by answer. So our current is equal to 0.14143 ampere. Let me confirm that. 0.62. Yeah, that's correct. Yeah, it's 0.143 ampere. But oh, sorry, I used 10 for my gravity. Use 9.8. If you use 9.8, you get 0.146 here. Because when you are doing your test or your exam, use 9.8. So let's move on. So that's the magnitude of the current. Now let's check the direction. Now the question says the current that is required to remove the tension. Now, if you use a wire to hold a mass, this wire we use it to hold this iron. So the tension is downward. You can see gravity acting downward here. The tension of this wire is downward. Am I communicating? So if I have a force acting downward, 8 Newton, if I want to remove this force, if I want to cancel it out, the force I will apply, will it also be downward? No, now. If I apply another force downward, that means everything downward is now 16 Newton. But for me to remove this tension that is coming down, I have to put a force that is opposite it. So the current required to remove the tension. Am I communicating? So we are also using, and this thing we are talking about, we are not talking of tension, we are talking of force. So we are also going to consider the force required to remove the tension. Am I communicating? So the force required to remove the tension will be going upward. Are we together? Since the tension is acting downward, the force required to remove it will be going upward. And what's the direction of our current? The direction of our current, we don't know it. That's what we have to find. The magnitude and direction of the current required to remove the tension. But since the tension is downward, we already know the direction of the force that can also remove it. Now, the direction of our field, I told you this one is going in when you see star, when you see dot is coming out. So if my force is upward and this is force F upward and my field B is inward, Now what will now be the direction of the current? Now, this is my finger. Force upward, field inward. That is into the page. Then what will now be the direction of the current? Now, this stands for field. Now, for this field to be going into the page, this is the field. See where the B is. Let this finger be going into your paper, into the page. And this force must be upward. Why this current? That's what I want to see. So for my field to be going into the page and oh my God, how can I stretch my hand now? Now this is it. This is it. Sorry. Let me do something like this. I'm coming. Let me just do something like this. Yeah. Yeah, I think it's good this way. So this is the field. My field going inward. For my field to go inward and my force to be upward, this is my finger. So you can see. Sorry. So I will allow this one to go inward and this one to be going upward. Definitely my current is going outward. Can you first push the finger and how it should be. This is how the finger should be. Are we together? This is how it should be. Now, now follow the direction. Field inward. This one, this is the field. Go into the paper. Force upward. This your force upward. This line, force upward. Now you can see your current will be going what? From the left to the right. Your current is going rightward. Whatever is facing your right hand is rightward. If it's facing your left hand, it's leftward. So this, your current is going to the right. So that's the direction of the current. So don't worry, let's do another question. You will understand better. Now, check this one. To get the magnitude, it's not even a problem now. Now, a metal wire of mass m equals to 1.5 kg slide without friction on I'm coming, let me just yeah. So I'm sorry, this is my room. So without friction on, sorry for the distraction. So without friction, the two horizontal rail space distance whatever, there our b equals to 24 mt. Pointing out of the plane, a constant we have d there to be 3 meter. A constant current I to be 12 ampere. I to be 12 ampere flows from a battery along one rail across the wire and back down the other rail. The wire starts moving from rest at t equals to 0. Find the direction and magnitude of the velocity of the wire. So how do we find to find the velocity is go far. Now let's do the magnitude first. F equals to what? QBV, right? Don't even Yeah, and what's F? F equals to, do we have F equals to mg? That means my mg equals to QBV. Am I given Q? Do I have Q? I'm trying to check something there. Yeah. So sorry. So yeah, I'm having a metal of 3 distance. The tracks in the vertical uniform magnetic field of this, pointing out of the plane, a constant current flows of the battery along the rail start to move. So I need to find my acceleration. Okay, F equals MA rather, MA. So my MA is equal to, do I have space horizontal rails on two horizontal rails, space a distance 3 meter apart. Okay, yeah. Sorry, I'm using BIL. So my force MA equals to what? BIL. Sorry. So what's the mass? I'm given 1.5 kg. 1.5 equals to, I have my B, 24 millitesla. Milli, that's times 10 raised power minus 3. Whenever you see small letter, M is milli. When you see capital letter, M is mega. What's my I? My I is what? My I is 12 ampere times, what's my L? That's the distance, 3 meter. Length of the conductor, something like that. 3 meter. Now, your A will now give you what? 24, this times this over 1.5. Now, you can just do that yourself. 24 times 10 raised to power minus 3 is equal to times 12 times 3 divided by 1.5. So my acceleration is equal to 0.576 times 10 raised to power 576 meter per second square. That's my acceleration. 0. Do you understand this? F equals to BIL and F is MA. So MA equals to BIL. That's what we did. Yeah. Then you make A the set of the formula. That's BIL over M. So 24 times 10 raised to power minus 3 times 12 times 3 divided by 1.5. Yeah, 0.576 meter per second. And that's the acceleration. Now for the velocity, we have to find the magnitude and direction of velocity. V is equal to u plus what? At. Since the guy is starting from rest, from t equals to 0. So u is equal to 0. V is equal to what? At. Then to find our velocities, from t equals to 0 to t equals to 5 seconds, according to the question, to time t equals to 5 seconds. So my v will give me 0.576 times 5 seconds. Are we together? Times 5. So here now my velocity is equal to what? 2.88 meter per second. So that's my velocity. Check the calculation very well. There's no problem about that. The main problem is on the direction. Why I'm not using QBV is because I can't just use it. We have two formula for force, QBV and BRL. I have the parameters for BRL in the question, so that's why I'm using BRL. F equals to BRL, and F is mass times acceleration. So just get it. Use this one to get your velocity. Now to check the direction. That's where the problem is. Now please take note. No, for BRL, this one stands for velocity. For BM, for stand for current. For QBV stand for velocity. Now it doesn't mean that whichever this thing your current is pointing to, then that is your velocity. You can see that our current is downward there. Then because the same finger that represents velocity represents current, doesn't mean that the direction of your current is same thing as the direction of your velocity. That's not what it's saying. It's saying whenever you are dealing with QBV, your forefinger stands for velocity. Whenever you are doing BIL, your forefinger stands for current. That's what it's just saying. It's not saying current and velocity have the same direction for a particular question. No. Just saying use your forefinger for velocity and use that same forefinger for current whenever you are dealing with that different kind of case. So you can't say because this current is downward, then your velocity is downward. That's totally rubbish. So how do you get the direction of your velocity? You can get the direction of your velocity by the direction of your force. Now from what we did, we say force is equal to ma. So the direction, the direction of our force is same thing as the direction of the acceleration, because this is a calculator. If I'm applying a force to push this calculator, the calculator will be accelerating to the direction of that force. I can't be pushing it and it's coming back. No. If there is nothing that is pushing it. So if I'm pushing it, if my force is going like this, it will be accelerating to that area too. So which means the direction of my force is same thing as the direction of acceleration. So now what combine velocity to acceleration? Now we say velocity is equal to what? U plus at. And since time t equals to 0, velocity is equal to at. Which means so far they have the same sign, positive, positive, which means the direction of my acceleration is same thing as the direction of velocity too. Note, no motion under gravity, we have v is equal to u minus gt. Do you get that? If it's moving upward. If it's moving downward, it's plus. If we have a case whereby it's moving upward, it's v is equal to u minus gt. So let's assume that it starts from rest. So v is equal to minus gt. So this one now, if my velocity is like this one will be like this because I have minus here. But the fact that plus plus, so whatever the direction of my acceleration is same thing as the direction of my velocity. So how do I get the direction of my acceleration? Is by getting the direction of the force. Do we get? So now let's find the direction of the force. Now this is the field. Dot is pointing inward. Pointing inward. See, anything you have, if it is plus plus plus, no, for electric potential, I said W is equal to minus change in kinetic energy. So this direction of this one will be opposite of this because of the sign minus. But if it is plus, like plus F here, plus MA here, the direction of the acceleration is same thing as the direction of the force. So this field is going inward, this one inward, current downward. Then what will be the direction of the force? Now, this thumb is the force, this is the field, and this is the current. So I'm coming. So for my field to be going inward and my current to be going downward, this one is for current. Now my field inward. Now this is the finger. Sorry. So my field inward, my current downward. Just stretch your finger first. Stretch it such that this one will be pointing upward. Stretch it first. Stretch it very well. So this is your field inward. Your current, this is the current to go downward. For the current to go downward, while the field is maintaining inward, you can see my field maintaining inward. That means your force is rightward. Can you see my thumb? Can you see now? For my field to be going inward and the current downward, see this is the current downward. Field. Oh, my field is outward, sorry. It's a dot. My field is outward, sorry. This is a dot, sorry. My field is outward. So for my field to be coming outward and my current downward, you can see my field is coming outward and my current going downward. See my field outward, my current downward. That means the force, my thumb, is leftward. The thing is simple. Just come for the physical tutorial on Saturday. You will get it very well. My field outward and my current downward. Then my thumb is leftward. Leftward. You can see. So if my force is leftward, my acceleration is also leftward and my velocity is also leftward. So that's that for that. Now we spend much time on this. Then the other question, I will just show you. You go and solve it yourself. Now, those of you who are using vector to find your direction, you are wasting time. Just understand the finger. You are good to go. Inside the cube, there is a magnetic field B directed upward. Find the direction of the magnetic force experienced by a proton entering the cube. A, that is entering the cube from the left, from the front, from whatever. So these are the proton. So if a proton is entering somewhere, that means the current is going the direction of the proton. Are we together? If it is electron now, the current will be opposite the direction of electron. Please take note. Current and electron, they move in opposite direction. But current and proton, they move in the same direction. Just get it like that. If you are convinced of proton, proton is positively charged. So current move in the same direction of. Do you understand what I'm saying? So if you have a positively charge that is moving to this side, so the current is also moving to that side. Are we together? And that's it. If you have a negative charge that is moving to this side, the current is moving to this side. Am I communicating? So, should I even say something like that? Hadn't be the state that is electron, the electron entering from the right. Okay, well, I think we don't need that. Let's just, okay, yeah, we need that. Sure, 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 sure. If an electron is entering from the left, then the current is going out. That's correct. But the fact that a proton is entering from the left, then the current is going in because the current move in the same direction with positive charge, move in opposite direction with negative charge. So that's that for that. Take note of that. Now this is proton, positive charge, going from the left. That means the current is entering. The current is entering from the left to the right like that. So now let's check the direction of the force. If my current is entering the cube, this is the direction of the current. Now, normally, I was not told the direction of the current. Do you know that? It's the direction of proton I'm being told by a proton entering the cube from the left. So how do I know that my current is also entering from the left? I've explained. When you have positively charged, the direction at which it's going will be the same direction as current. When you have negatively charged, the direction of the current is opposite the direction. So far as positively charged, it's entering from the left, that means the current is entering. This magnetic field direction remain constant throughout the whole case. If field is going up and current is going to the right, the way you are facing your phone now, the way you are facing your phone or your book is your right. This is your right. You are not turning your back. You are facing it. So this is your right. This upward. So what will be the direction of my force? If my current is rightward, my field is upward, then my force will be where? This current, rightward. This field, upward. Where will be this thumb be? You are not. If you use your left hand, you will miss it too. You are using right hand. This is Fleming's right hand rule for crying out loud. So for my field to be upward and my